Today we're going to talk about related rates. So here's the idea behind related rates. I have a bottle of water in my hand. What would happen if I started spilling the water? There'd be less water in my bottle, that's true. What else would happen? Water would be on the floor. And what would happen to the water on the floor? It would spread out. If the floor were perfectly smooth and perfectly level, and I poured water onto the floor, what shape would I get? You would get a circle. And what would happen as I poured more water out? The circle would get bigger. Grace?
Wouldn't it only be a circle if you were pouring the water out at exactly the same rate?
No. That's the whole point. If I pour the water out slowly, what's going to happen to the circle? It's going to grow, but it's going to grow very slowly. If I pour the water really fast, what's going to happen to the circle? It's going to get bigger really fast. Right. Well, if I pour the water out, I'm going to get some sort of object. The only way I would get a circle would be if the floor were perfectly level and there was no friction. So in theory, I could get a circle, but in reality, I won't.
But your hand was shaking a little bit, and then you pour here.
Oh, no, my hand is perfectly steady, and I'm pouring right down the middle. My hand never moves.
You have to be on center for circling. And there's no splash damage either.
Well, the circle would start right in the center. And there's no splash damage either, correct. No splashing. All right, so it's a theoretical thing. But my point is, if I pour the water fast, the circle's going to grow fast. If I pour the water slow, the circle's going to grow slowly. Correct. So those are related. Those are what we call related rates. How quickly the circle grows depends on how fast I pour the water. And that's what we mean by related rates. So related rates, we're going to have a couple of things moving at the same time. And their movements will be related. And we're going to look at formulas and some problems and solve these sort of things. All right, so related rates are derivatives. What does a derivative usually tell us?
Slope.
Tells us the slope of the tangent line, correct.
Rate of change.
Which happens to be rate of change of the graph. Or we have seen that if our original function is a position function, what does a derivative tell us? It tells you velocity. And velocity is the rate of change of position. Velocity is how fast your position is changing. So, first just some terminology here. The rate of change of x with respect to t. I want you to take that sentence and write a math symbol for it. What do I mean by the rate of change of x with respect to t? Rate of change tells you I need a derivative. The right answer in this class is almost always derivative. Rate of change is a derivative. So what do I mean when I say the rate of change of x with respect to t? That would be dx over dt. So in this case, most of our derivatives are going to have dt on bottom, many of them, because t stands for time. So what I would be looking at here is I have something moving on the x-axis maybe, and I want to know how fast is it moving at a particular time. So I want to know how fast is x changing at some time, and that would be the symbol for that, dx dt. How fast is the sale of houses changing at that instant of time? Okay, the key words are, you see, fast and changing. Those two words mean?
Derivative.
The right answer in this class is almost always derivative. That's correct. That means derivative. Derivative of what? The derivative of sales of houses. So we got to figure out what letter we want to use for sales of houses. What letter do you like? S. So we're looking at the change of the sales in houses. That's ds. At that instant of time, dt. Again, our bottoms now for these problems are almost always going to be dt. We're almost always looking at how fast something changes in time. Yes?
You were doing instant, or you mean taking the second derivative? Or you were doing the instantaneous?
No, instantaneous rate of change is the first derivative. Average rate of change is your old slope formula, y2 minus y1 over x2 minus x1. So here we're always looking for instantaneous rate of change, not average. So we're always going to be doing derivatives. Always. Number 3, the radius is decreasing at the rate of 4 centimeters per second. Okay, so I need a symbol for the radius is decreasing. The word rate tells you you have a derivative. So how do I write the derivative of radius? I'm going to use r for radius. So dr dt equals -4. Excellent. Why is it -4? Because it's decreasing. So when you see the word decreasing, your derivative will be negative. When you see increasing, your derivative will be positive. Okay? Time for a few more here. The supply of tapes is changing at a rate of 10 packs per week. So again, the things you see are changing. Rate. Those words tell you derivative. Derivative of what? C for cassette tapes. So dc dt. Very good. You would not want to use dt over dt because that would be confusing. I agree. Equals 10, I guess. It didn't tell us it was decreasing. If it didn't tell us it's decreasing, I'm going to assume it's increasing. Now you could use dt if you used like so. In math is case sensitive. So capital T would mean something different than little t. Yes? Should we put units? You're darn right we should put units. Units will be very important. Oops. Absolutely there should be units written. Units will be very important when we get into the word problems. The first two, there was no number given. So there's no units to give. So I wouldn't put units there. Number 5, the area of a circle is increasing at a rate of 9 pi inches squared per minute. dA, you're going to use A for area, okay? So I would use a capital A. Usually area is capital A. Would it be wrong to use a little a? No. dA over dt equals 9 pi inches squared per minute. Very good. All right, so now here's the sort of word problems you're going to see. So those are just warm-ups on how to write the symbols. Pancake batter is being poured into a pan to form a circular pancake, so it's kind of like dumping my water on the floor, whose area increases at the rate of 3 centimeters squared per second. How fast is the radius increasing when the radius of the pancake is 5 centimeters? All right, so the first thing we need to do is we need to read through the problem and understand what they gave us and also understand what we're looking for. So what did they give us? They gave you dA dt, excellent, because you see, correct. They gave us dA dt because it says area increases at the rate. The word rate, that tells you right there that's a derivative. So they gave us dA dt equals 3 centimeters squared per second. That was something they gave us. What else?
They gave us the radius bar,
They gave us what the radius is. You were correct. The radius is going to be, radius of the pancake is 5 centimeters. So they told us, is that dr dt? Is that a derivative? No, how do you know that one's not a derivative? It didn't say rate. It didn't say changing. That's a fixed value. So the rate, or the radius, I mean, is 5 centimeters. So I think those are the two things they gave us. Now what are we trying to find? How fast is the radius increasing? So again, I see fast, which tells me something's changing, increasing, something's changing. So I'm looking for derivative of radius. How fast is the radius changing? So I'm trying to find dr dt. All right, so there's what they gave us, and there's what we're looking for. Now what I need a formula that relates the variable A with the variable R. Do I know a formula that relates the variable A with the variable R? And we're dealing with a circle, so we should know the formula for area of a circle. The area of a circle is not 2 pi r? No, 2 pi r is circumference, you're right. Area equals pi r squared. Interestingly enough,
Now, does that work with every single one? Like that, like it does. Isn't it work with the perimeter is always the derivative of the area, and then the area is always the derivative of volume?
no. I believe that only works for circles and spheres. It doesn't work for shapes of other objects. But it does happen to work for circles and spheres. If I take the derivative now, what's the derivative of A? Nope. 1 dA dt. What's our underlying variable in all these problems? We're trying to find, we know dA dt. Our underlying variable in these problems is always time. How fast is something changing with respect to time? So whenever I take the derivative of an A, I'm going to write dA dt. And over here I take the derivative of pi r squared. The derivative of pi r squared is 2 pi r. That's almost correct. dr dt. It's always a chain rule thing. Whenever you take a derivative here, our underlying variable is always t. We always have to use the chain rule. So we have to have a dr dt right there. It's interesting that if you start with the area formula, area is pi r squared, you take the derivative, you get 2 pi r, you get the circumference formula. That is interesting. And I think the same thing works for a sphere. If you start with the volume of a sphere and you take its derivative, I think you get its surface area. It's interesting. Okay, we're almost done now. Now what do we do? Plug in, check what I know. Do I know dA dt? Yes, dA dt is 3. Equals 2 pi. Do I know r? Yes, r is 5. Do I know dr dt? No, that's what I'm trying to figure out, isn't it? So now I can find dr dt very easily. To find dr dt, so it's going to be 3 over 10 pi equals dr dt. But I should put units on there. What would my units be?
Centimeters per second. Centimeters squared.
Centimeters or centimeter squared? Radius is in just centimeters. How come?
Because, well,
It's linear. Radius is a linear distance. Linear things are feet, inches, miles, centimeters, meters, those sort of things. Area comes in square units, centimeters squared, feet squared, so on and so forth. All right, so the units here should be centimeters per second. Questions on that one? All right, I think we got time for one more maybe. There it is. Suppose the quantity X of Super Titan radial tires made available per week in the marketplace by the Titan Tire Company, that's hard to say for some reason, is related to the unit selling price by the equation P minus 1/2 X squared equals 48, where X is measured in thousands of units and P is in dollars. Asked is the weekly supply of Super Titan radial tires being introduced into the marketplace when X equals 6, P equals 66, and the price per tire is decreasing at a rate of $3 per week. Well, the good news for this problem is they gave us the equation. Word problems are almost always easier when they give you an equation and you don't have to figure it out. So we know the equation, P minus 1/2 X squared equals 48. What else do we know? Changing of the rate of what? So we know the price per tire is decreasing at a rate of. So what symbol is that? dP over dt is -3, it's decreasing. We know x is 6. We know p is 66. What are we trying to find? We're trying to find how fast is the supply changing. So the supply would be, the supply changing, I agree, that would be dx dt. Well, this one's pretty straightforward, I think. It gave us the equation. I think we have everything we need. We go ahead and we take derivatives. So I'm going to start with p minus 1/2 x squared equals 48. What's the derivative of p? dp dt. Minus, what's the derivative of 1/2 x squared? 2x?
X, sorry. X.
2x? 2x is partially correct. There's more. Not times 1/2. Oh, times 1/2, that is correct.
So it fills it with
Just makes it just x. Still something missing. dx dt. Anytime you take a derivative here, you're going to have a d something dt. dx dt. Derivative of 48? 0. All right, so I plug my numbers in. P dp dt is -3 minus 6 dx dt equals 0. Move the 3 over, so -6 dx dt is 3, so dx dt is -1/2. And what would the units be? Tires per week? Dollars per week.
They're asking how fast the supply is.
So in this problem, which one is dollars? P is dollars, P is price. So dx dt is measured in tires per week. But it would actually be thousands of tires per week, wouldn't it be? So it wouldn't actually be half of a tire per week. It would really be 500 tires per week. So the supply would be decreasing by 500 tires per week. So -1/2, I don't know how to write thousands tires per week. That's kind of a weird unit. -1/2 of 1,000. It would be a lot more cleaner if I just wrote -500.
Where'd the 2x come from?
The 2x came from the derivative of x squared. I brought the 2 down, subtracted 1 from my power. I forgot I needed to write the 1/2. The 1/2 should have probably been first. The 1/2 just stays.
It's not 1/2 x squared.
No, well, the original function was 1/2 x squared.
Right.
But when I take the derivative, this 2 comes down front. That's where that 2 came from.
Does it come down and multiply with the 1/2?
Uh-huh. 2 times 1/2 gives 1. Yeah, I wrote the 1/2 in the wrong place, which is why it was. I forgot I needed the 1/2.
So where did the -6 come from?
Where did the -6 come from? X was 6,
Ah.
so I plugged in 6 for x, and I canceled the 2 in the 1/2. Robert.
Except like the road supply decreasing by 500 tires per week.
Absolutely, I would accept supply decreasing by 500 tires per week. That would be much better than what I wrote, I think. Much better. All right, so bring this with you tomorrow. Tomorrow we'll go through the rest of these problems, see what those are like.